So welcome everyone to this new lecture. I am consistently late with the recording. I'm sorry, I know. I'm really doing my best to get better at this, but it's just an overwhelming amount of work to actually get everything correct. But I hope that with time this is getting a bit better. So this time it's hopefully better than last time, at least by day. So today we continue talking about life as a thread, basically, and what does a thread life cycle look like on different environments. We will actually cover in much more details the way that Linux handles this in the exact next video. But this is more of a general overview of threading in general operating systems, just so that you guys get an idea of threading in general. So as per your request, I start by saying that this is basically from section 4.3 to section 4.7 in the book. So read until section 4.7. Actually, you can read the remaining parts, section 4.8, which is not a long read, but we will cover a lot of section 4.8 in more details in the Linux, when talking about the Linux kernel code. And I'm not sure if I mean, it will give you a general overview of again kernels in general, but it will not be super spot on what we are going to discuss later anyway. And I think that the Linux way is much more elegant. I will also touch upon the Windows way in when I'm explaining how Linux works. So with this, I hope that you will enjoy today's lecture, and let's continue from here. In the last lecture, we ended by talking about the fork join, the way that basically threads have fork and join and how fork and join works. We had actually during the last lecture even played a bit with fork. Today we are going to talk into more details about how thread actually is implemented in most operating systems. So first of all, a thread has what is called a thread control block, and the thread control block is basically something very similar to the process control block that we learned about earlier, the PCB. It's basically a data structure that stores all the states of the performant computation. So if you're running a long program, what line are you in, and so on and so forth. So it basically stores also, for example, your variables, your thread variables. It stores data that is required for the management of the thread. So for thread scheduling, which we'll talk about into much more details pretty soon, as in I think 1 or 2 lectures from now. It helps in these things. It stores data that is required by these for scheduling, basically. Then you have the stack information also stored, and it stores what functions or methods are running in the thread, because the thread is basically a program, so it can have multiple functions, multiple methods, multiple procedures, depending on what application you're actually running, right? So, and depending on the programming language you have been using also. Whenever a new thread is started, you basically allocate some part of the memory in a very similar way to the PCB. You basically have a heap and stack for per thread, and that is basically used for the thread to function, to do what it is supposed to do. And of course, all of these, the pointers to these are stored in the TCB, just like the case with the process control blocks. So, I have a question here. Do you think that we can have one single stack for all threads? Can we basically just have a single stack for all the threads if you have 1,000 threads running on your computer that are doing different things? Is it wise to have a single stack for all of them? Okay, so the PCB basically also when a thread gets suspended or evicted because, well, because of an hardware interrupt, for example, because it has already been running for a long period of time or something like that. You save the registers of your thread in your TCB, your thread control block. You save the state of the processor, registers such as which part of the instructions are you in, the instruction pointers, and so on. The actual implementation is very operating system specific. It also depends quite a bit on the actual hardware that you're running on. I mean, what your choice basically to your design decision is influenced by both your hardware and the whole operating system in general. And the way you implement the TCB is also different in different operating systems, of course. You either have the saved registers as part of the stack or have a separate space in the TCB for this. So you basically, when storing the saved registers after being evicted, you have a choice to basically have it either in the thread stack, stored in the thread stack, which is basically a chunk of memory that's allocated to the thread, or on the TCB, which basically stores all data that the thread needs. There is, of course, per thread metadata also that you have on your TCB, such as your thread ID. So you can have, I mean, it's equivalent to the PID, which we have been looking at for the processes, for example. You can have different scheduling priorities, and you can basically have a thread that is waiting for some input or ready to run later. You can have threads also with shared states. So basically, if you have 100 threads that all run the same program, which is, let us give an example with the web server. I mean, if you have an Apache web server, basically the handler for each request is roughly the same. I mean, you're running basically some, I mean, it can be, of course, anything that is beside worldwide HTTP, but I mean, you have some sort of server that handles incoming requests from different clients. And these requests can be FTPs, can be HTTPs, or something, depending on basically the software that is running on the server. But for an Apache web server, you basically have something that, well, replies for a GET with some, you have some procedure to do a GET, some procedure to do a POST, and so on. So you are sort of running the exact same code for each request that you receive. And that's basically shared state. So that program code is one of the shared state. But also you can have global variables, like in any programming language, you can specify some variables to be global. They become very hard to manage when you're talking about concurrency, about threads, because basically if you have global variables that are being changed by multiple threads at the same time, you want some way to basically make sure that there is consistency when changing the variables. Okay. Now, what space is a normal thread running in? It's usually running in the user space. There are kernel threads that we'll talk about in more details. The question is if a thread can corrupt the data of another thread, and again, this is highly dependent on how you implement things. So if you have multiple threads having shared states, then you need some locking mechanism on that. We'll talk about that in the next lecture, actually, synchronization mechanisms. But also, I mean, you are not supposed to be able to touch other threads that do not share state with you. Their memory, for example, you're not supposed to touch their data. So let's look at how a thread actually runs and its life cycle. So a thread basically starts by some process calling the thread creation. That process can be init, which is basically the first process that is running on Linux, but it can be another process. So let's say a web server, for example, where you're serving multiple requests, and you basically call thread create to create a new request handler to handle a new request that is coming to your web server. And once the thread is created, the thread doesn't run directly. It goes into basically a data structure that stores all threads that are ready to run, but that have not been allocated CPU time yet, or basically compute time yet. So the thread starts in the ready state and is stored in this data structure. Now, the reason that you do that is that, well, you might not want the thread to run right away. You might want it to sleep for a while or something. But then you schedule the thread to run, and that can be basically because it's the scheduler decides that it's time for this thread to run, and it starts running, doing whatever it is supposed to do. But then a thread that is running has one of three options. It either exits, and that basically occurs when you have it basically occurs when you have the computer, the CPU finishing what it is supposed to do, and the process ending, basically the thread ending. And if it's the first time that the thread runs on the CPU, it's very atypical to basically go from running to exit right away, because otherwise it's a really short, it would be a really short running thread, because the CPU time that gets allocated per thread is not that much. I mean, it can be in the order of milliseconds or even microseconds sometimes. A thread that is running might basically, after doing some stuff, need to fetch data from memory or need to fetch data from hard disk, and that basically means that it needs some I/O. Or it can be just waiting for me to move my cursor, my mouse cursor. And in that case, the thread basically calls thread wait, and the thread wait puts the thread into some waiting state and basically waiting for something to happen. And that thing is typically some I/O that you need, or some, you send the data to a co-processor, for example, if you have two processors, and you're waiting for the answer, or something on that order. Once that event happened, it can be also that you're waiting for communication from another thread, right, running on a different processor, or waiting for some result of some computation that another thread will produce, or waiting for a network event, for example. So in general, you stay in the waiting state until that event happens. So suppose that you have that thread as listening, waiting for a network packet to come, basically. Then once a network packet comes, then the thread basically uses thread join and goes to the ready state again. Okay, and then from the ready it gets scheduled again. So this path is basically governed. This path happens when the thread needs to wait for something. Okay, but the scheduler might also suspend the thread by calling thread yield and put the thread from running state to ready state, while the thread having everything it needs to run, but well, there's not enough processor time for it, or it just got deprioritized for something, you got an interrupt or something. And this is basically the thread life cycle. When there are no threads in the system, there is an idle thread. And that's basically a thread that gets scheduled when there is absolutely nothing on your computer to do. And that is, you can, in theory, implement a zero-threaded kernel, but it's not very easy because of the way the hardware works. A processor is basically an electronic device with electronic gates, and as an electronic device with electronic gates, it needs to voltage and clock to be up. And they do that one way to basically ensure that you're not losing voltage, and you're not basically going into a state where your clock is mismatched with the actual clock or something, is to basically not allow the computer to do nothing. You basically put an idle thread, and using that idle thread, you will have one thread per processor, one idle thread per processor. In very modern architectures, what happens is when you have an idle thread is that you put also the processor on a low power sleep mode when the idle thread runs. And that basically makes the processor go into, reduce the amount of power that is used and so on. Then the idle thread is the lowest priority thread that you can ever have, because you do not want the idle thread, for example, to be scheduled every now and then. The processor, if the processor has 1,000 other actual threads to run, why should it go and run an idle thread that basically does nothing, right? So the idle thread has the lowest priority ever in your whole system. And in doing that, you basically make sure that your processor is, the electronics are up and running in a more easy way. But also you make sure that the idle thread does not interfere with the normal operation of your processor or of your scheduling. So let's talk a bit more about how threads are actually implemented. And one way of implementing kernels is basically to implement them as kernel threads that are only available for the kernel. And that basically means that the kernel can control everything about the threading, but still might give the user some control of some of the data, for example. To the kernel, basically, kernel thread is nothing more than a single-threaded user process. It's just a process where nothing runs inside. And the way that multi-processes are implemented in many operating systems, including Linux and Mac OS, is that you have them implemented using kernel threads. So you have the kernel threads that run inside the kernel, and you expose some of the functionality using system calls. So as a process, as basically user level process, you can call a system call to fork a new thread, for example, to start a new thread. But then what would happen is that the system internally will implement everything, or will basically spawn the new thread for you, and the kernel will control that thread. But it will give you back some of whatever is needed. If that thread is only supposed to run, for example, in user space, because, well, user space function just called it, then it will run as user space thread. As user space thread, by giving it privileges equivalent to user space thread. You can also have user level threads, user space level threads, and these would be thread operations without system calls, basically. But at least Linux and Mac OS do not work that way. So let's look at this figure, where you have code, for example, and you have multiple kernel threads in the kernel, running in the kernel, but you have user level processes trying to spawn new thread, and process 1 has thread 1 and process 2 has another thread. And basically, to the way that the process deals with kernel level threads is that it invokes a system call, and the system call basically the kernel handles this and starts a new thread for this process, with basically having only one single thread per one of these processes, but making sure that, well, these threads do not violate what they are allowed to do. Multi-threaded processes are a bit more complex, because the previous one just had one single thread spawned. Now, if you have a multi-threaded process, basically, then again you basically use system calls to start a couple of these or many threads as a user, and then the process control block and the the thread control block for each of your threads are stored in the kernel space, as you see here. And basically, you then manage the way that you relate, for example, you manage memory and these things in using the process control block. What memory is this process, is this thread allowed to touch? What memory is it not allowed to touch, and so on and so forth in the kernel itself. And then when you actually do the real scheduling, you'll run this thread for a while, this thread for a while, this thread for a while, but then you'll start running this process. But in that process, you just run one thread, right? If you have just one single processor, you run just one thread, and after a while, you might actually have an interrupt, or that can be basically because you ran for a long period, and then you basically need to have an interrupt stack per thread, so that you save whatever data you have and whatever state you have to be usable again, because then you will basically start scheduling this kernel thread, for example, this kernel thread, for example, and so on and so forth. So you need to keep an interrupt stack for every single thread. This is how a very naive implementation of kernel threads would look like. It's actually, well, it's pseudocode, so it's not implementation. You cannot say it's implementation. Basically, you can see that you create a new thread control block, and you basically also create a new stack, basically saying that this is the stack size and this is the stack base. And the stack base is basically the memory address that you start the stack for this thread, and then the stack size is how much memory can this thread use. And then you start initializing some registers, such as your stack pointer, right? So you want stack pointer, which points basically to which part of the stack you're in. You want to set the instruction pointer to, well, basically when you start, what instruction do you start with, and you want to set some registers that you need, and then you move that thread into the ready state, so that, well, you can run it if there is if it's time for it, if it gets scheduled basically on the on the processor. Now let us inspect this code. This code a bit more. So when you create the thread, you basically pass to that thread what function that thread is going to run. But when you look at this, you basically set up a few registers, a few pointers here and there. But this is something that we should talk a bit more about. So you basically set an instruction pointer to stop. And what you're doing is that you're not really calling the function that you're passing to the thread directly, but rather making a stop that basically calls the function from the stop. And stop function, I mean, you know what a stop function is. It's a dummy function basically, but in this case it's a dummy function that basically calls function. So you do not call the function directly, but you rather have the instruction pointer not pointing towards the function, but pointing towards the stop, because that function, you can point basically the instruction, you could have pointed the instruction pointer to function instead. And that you set the arguments that basically to stop. I mean, this is basically now your register. So you set the arguments to stop to be a function, telling the stop function that the stop function will to call func, and you set the arguments to arg basically. And that what does this do is that it basically goes in here and calls function, and calls function with exactly the same arguments that you're passing to the thread. Okay, then why do you have this extra level of indirection? It seems quite counter intuitive, but the reason is that you might implement a function, you might pass a function to a thread that does not call thread exit. And that would be very problematic, right? Because thread exit is the way that, well, you know that the thread has exited. Otherwise, you have a thread that is in limbo state. So for security reasons, what you want is that you want to make sure that whatever crap the programmer provides you to your thread, it basically finishes and terminates correctly. It does not just litter your system, or it does not do something stupid. Okay, so if you don't call, if you didn't have thread exit, that would mean that you return to whatever random location is stored in the top of the stack, because, well, the thread has finished running and then you need to return somewhere, and thread exit is the way that which basically tells you where to return. So you basically have this extra level, and after calling function func in the stop, you basically call thread exit, and basically making sure that the thread exits properly. Now, if func has already called thread exit, then you basically will thread exit, and you'll terminate the thread, and then everything is fine, because, well, you're not going to return anywhere. You're going to return with the first thread exit. Okay, so now let's talk about how we delete a thread. A thread basically cannot delete itself when done. I mean, when a thread is done, you should never allow a thread to delete itself, because it's actually, I mean, thread deleting itself is just like a person killing himself in some sense. It can lead to catastrophes. It's much better to basically get killed if you have insurance by someone else than to kill yourself. And it's quite similar in your Linux system. You need something else. You need an extra thread. You need someone to basically make sure that everything is clean, the memory is clean, there are no memory leaks, there are no memory corruptions, and the memory is fully released, and so on. And one of the reasons that you might get memory leaks or memory corruptions is that while thread is killing itself, if suppose that you come up and say, no, this is inefficient, I want thread to delete itself. So suppose that a thread is deleting itself and then an interrupt happens right in between. That would basically mean that the thread is neither deleted, but since it has already started the procedure of deleting itself, then it might have already, I mean, it becomes in a quasi-state, in a limbo land, where it's not fully deleted, but it's not actually also there. And that basically means that there's no way to clean this up. And if you say that, well, I can do things differently, I can organize deleting a thread differently from what it is currently done and more efficiently, the question will always boil down to this: an interrupt can come at any point, and if an interrupt comes, then you are completely, I mean, and that interrupt can have a higher priority than you, because there are things that have higher priority than the thread that is running in user space. And basically the TCP, the thread control block, is the only way the thread and the processor knows where things are. So basically, if a thread wants to, if we go back to this figure, if a thread is done running and it wants to exit, it calls thread exit and goes into a finished state. It does not kill itself. And then once in a finished state, the thread moves the thread control block from the ready list to a list of finished threads. So everything now is on the finished threads. And then you have sort of a garbage collector, if I may say, that basically that is another thread that gets the task of actually moving the data, making sure that data that needs to be stored is stored properly, and so on. And it goes through the finished threads continuously. So, as a thread, you basically can leave the processor in two cases. So if you're already scheduled on a processor, if you're already in a running state, you can leave with basically, I mean, we had like the 3 errors, right? But you can leave either voluntary or involuntary. And voluntary is basically using thread yield, thread join, or thread exit. So you're basically evicting the processor or the leaving the resources for other threads to get processor time voluntary. You're basically giving up your share. And thread exit, well, it's basically when you're exiting, I mean, you're done with whatever you're supposed to do, so the code is over, it's finished. So you exit, and you go to the exit state, the finished state, and you basically leave the processor. Thread join is when basically a parent thread or a parent process decides that it will wait for the children to finish, or for one of the children to finish. Thread yield is basically when the process itself decides that now I should basically leave the processor for because I'm waiting on I/O, I'm blocked on something, I'm waiting for input from the user or something. Involuntary thread context switching happens basically when similar to what happens in processes, is when you get an interrupt or when you get a processor exception. And these are basically the two ways that you get thread context switching. When you do thread context switching, what happens is that you save the registers of the old one of the old thread on the stack, on the old threads stack. You switch to the new stack, basically to the thread that it comes. If I'm going back here. So you basically pick a thread from here that is going to get scheduled, okay, and you basically switch to the stack of this thread, right? Yeah. And you restore the registers from the new stack, anything, because that was basically something that got interrupted before, or that is something that is just going to run for the first time. And when you return to the new thread, when you basically start running the new thread, you do not return to the thread yield, so you do not return to where the thread actually called yield, but you rather return to wherever the new thread needs to start, because you do not, otherwise you will loop. If you return to thread yield, then you will basically loop, because I call thread yield, I should go back, and you will keep doing that. And there is no difference between kernel threads and user threads on this. Involuntary kernel switching is very similar to what we described earlier. Basically, slide 21 and further in the kernel abstraction lecture. There's, I cannot recall the exact date, but I think the slide deck names is lecture 2. And there are a few differences though, because in the previous slides or in the previous description, we were talking about processes, and we were more talking about threads, and we were talking about switching in processes and basically from user mode to kernel mode. Now we're talking about switching and from kernel mode to user mode, but now we're rather talking about switching kernel threads. And the difference basically comes from the word kernel threads, because we are running at the kernel already. So there is absolutely no need to switch to kernel mode as you are already there. So you basically don't need to do the stack pointer changes that we described previously. And then previously we also talked about resuming the processes from the ready list. Now you basically all the threads that are in the ready list in the kernel stack are all kernel processes, right? So since they are all kernel level processes, they are all running in kernel mode, they are all kernel threads, you can run any of them. Okay? So that's what is the main differences. Now, it seems quite a redundancy that we talked about the PCB and the TCB. I mean, you have a process control block and you have a thread control block. Now, and I mean, what is the difference? Well, let me say that the operating system dictates the difference. It's very dependent from one to the other. But in theory, that includes Windows, for example. The PCB has more information about the process address space. So it basically has an information about the process, all its children, and things as such. And you basically need this information to do the context switching from one process to another, or between the process and the kernel, and to know basically the virtual memory mappings, the correct virtual memory mappings, and make sure that they are used. And that is basically the most fundamental difference you can say. In reality, for the kernel, the ready list basically contains a mix of PCBs for processes and TCBs for kernel threads. So in reality, what you're going to schedule is basically PCBs or TCBs. It doesn't really matter. It's to the processor. It's just a chunk of code. It's just an abstraction that you have added. It's just a layer of abstraction that you have added. And as I said, this is very operating system dependent. And as we are going to see in the next few videos or in the next video basically, I'm going to talk more about the Linux kernel philosophy on that. And the Linux kernel basically makes absolutely no differentiation between threads and processes, except that threads basically are processes that share some memory. And that's very elegant, very clean, and extremely efficient. I mean, starting a process in Linux used to be faster than starting a thread in Windows. Okay, things are changing, but this is how things were at least until I think Windows 8 even. So with this I conclude this part of the lecture. I will in the next video talk a bit more about the Linux, how Linux deals with threading and the internals. I will also, following that, I will talk about synchronization, and following that, I will talk about scheduling. A few comments that people have asked for. Well, the assignment 1 has deadline on the 2nd of December. We are lagging by 1 lecture already. I'm going to catch up while not basically making very long videos or making very long lectures. I hope that we keep the lectures, the video lectures even below 2 hours in most cases. That's basically the first thing that I wanted to say. I wanted also to say that there is a Slack group. I've never used Slack myself. I think it's called Slack, but I might be wrong. That I'm going to forward by email to all of you so that you basically communicate on this course. So with this I conclude. Thank you for watching this and see you on Friday.